Hello dear students, welcome to the lecture 10 of Artificial Intelligence and Machine Learning course. Today's topic is ranking.
An aside, text classification.
Okay, so we have text documents and we want to rank them. By the way, when we use the ranking word, it is not about ranking them by some sort of integer or number. We would rank them based on their similarity to each other or based on the query that we have. So ranking here is used in the sense of comparison of different objects, more likely. Okay. So we have text rave data and we have features of these documents such as Clinton said Pinot repeatedly last week on TV, Pinot, and we would have the feature set as like this. By the way, the values of features are here as binary. Therefore, if it exists, it has 1. If it is not, it is 0. So this is the binary way of existence of feature or not in the vectorial form. And you see it is called as occurrence of words. Okay.
Frequency of word occurrences. The most used weighting algorithm is Tf Idf term frequency inverse document frequency.
Okay, so you see you can use either occurrence of words as binary 1 or 0. You can use frequency of word occurrences such as 4, 1, 1, 0, 0, 1. Or you can use Tf Idf. We have already shown what is Tf Idf in the previous lectures. Okay. So how can we rank different documents? Okay, this is about that. As I said, the ranking here used for the calculating similarity or distance between documents. For decision trees for text, when we use decision trees for text,
each internal node represents whether or not the text has a particular word.
Or not. Okay, so this is the decision tree for text documents. By the way, decision tree is not good for very high number of features having problems. If your problem is very high dimensional, decision trees is not good for you. You know that in text document, in text classification or clustering, each word is a feature and is a dimension in high dimensional space. Therefore, for text classification, text clustering and text processing, the decision trees are not the best algorithm. Okay. Okay. So printing out decision trees such as with this one and predict not with export. Okay, anyway. So suggest a simpler word for the word below vital. And when we suggest a simpler word for the word below vital, you see important frequency 13. How is this calculated? This may have been calculated by scan the documents that have vital keyword and then calculate the frequencies of other documents in that vital having document, and then whichever has the most frequency, you may rank them. Okay, so important keyword has the maximum frequency in the documents that have vital word. In this case, it may have worked well. Okay. For accurate keyword, you see gotten, received, gained, and such. So here the training data and list of synonyms ranker list ranked by simplicity, and it may work in your data set or it may not work. However, in each problem, in each case, you have to decide your ranking algorithm. Okay, one wouldn't work in every algorithm. All right. So you see there are training data, ranker, and ranking ordering examples. And what about real world ranking problems? You see Netflix ranks movies based on your previous movies activity, and then shows you the suggested lists. Ranking is everywhere basically in our real life applications. In web search, Google ranks documents related to your query and tries to bring you the most related results according to your query. However, there are so many parameters in Google. For example, it checks your search history, it checks your browser, your location. I don't know, so many they have. And ranking applications, re-ranking and best output list, machine translation, computational biology, parsing, flight search, and black box approach to ranking abstraction. We have a generic binary classifier. How can we use it to solve our new problem? Okay, so our new problem is ranking and we have binary classifier. In that case, how can we rank documents and our query or such? Predict whether versus worse.
Train a classifier to decide if the first input is better than second. Consider all possible pairings of the examples in a ranking. Label as positive if the first example is higher ranked, negative otherwise.
Okay.
Predict better versus worse.
You see, in this case, each document is paired and ranked, and with this approach, we can rank all the documents even with binary classifier. Okay, there are combined feature vector. Many approaches will depend on domain and classifier. Two common approaches are difference and greater or less than otherwise. Okay. Okay, I think I will continue the lesson from other articles because these are not very good. Okay. Okay, you see, there is a PhD thesis related to new weighting schemes for document ranking and ranked query suggestion. You see, this is a really important topic and a hard topic actually. You can even write a PhD, you can even write a PhD thesis about it. It is not just that simple. However, I will try to find some simple example for you to make you understand. Let's find Tf Idf query document ranking. I think this would be a good example. Okay, let's start working on this. This page has so many ads. One moment. It is even slowing down my page load. Okay, so those ads are removed. They were slowing down my page load.
Tf Idf model for page ranking. Tf Idf stands for term frequency inverse document frequency. The Tf Idf weight is a weight often used in information retrieval and text mining. Variations of the Tf Idf weighting scheme are often used by search engines in scoring and ranking a document's relevance given a query. This weight is a statistical measure used to evaluate how important a word is to a document in a collection or corpus. The importance increases proportionally to the number of times a word appears in the document but is offset by the frequency of the word in the corpus data set.
Okay, so you see the importance increases proportional to the number of times word appears in the document. Okay. However, its importance decreases by the offset of the frequency of the word in the corpus. So, for example, the keyword of. This would be almost in every document. Okay. Therefore, its importance wouldn't be much, because every document would contain the keyword R, the word R or of. These are called as I think stop words, because they don't mean much for that document's let's say topic. You see, these are the stop words usually removed from documents when you are doing text processing. Why we remove them? Because these words does not tell us about the document. Okay, these are more like the generic words. They don't make a document specialized in any area, in any topic. So we remove stop words in documents before we work on them usually.
How to compute.
Let's check first whether this is a good example or not. Okay, yes, this is a good example.
Tf Idf is a weighting scheme that assigns each term in a document a weight based on its term frequency, Tf, and inverse document frequency, Idf. The terms with higher weight scores are considered to be more important. Typically, the Tf Idf weight is composed by two terms. Normalized term frequency, Tf. Inverse document frequency, IDF. Let's us take three documents to show how this works.
Okay, so we think as we have three documents and we will run a query, and then we will rank these documents according to our query, and we will show the user most relevant documents with an order. So we will do a ranking based on the relevance to the query, and we will use Tf Idf scheme to make this work. Okay, this can be also your project. You may You may use Tf Idf weighting ranking in your project. Okay, so the first document is
Ben studies about computers in computer lab.
so the second document is
Steve teaches at Brown University.
and the third
Data
document.
scientists work on large datasets.
By the way, the size of the documents is not important. Okay, the same approach, the same algorithm, the same methodology applies even if you have millions of documents, even if your documents are hundreds of thousands of words or not. It doesn't matter. The methodology, the system is same. Okay, in all cases, and
Let's say we are doing a search on these documents with the following query. Data scientists.
okay, so you can consider this query as another document. Okay, so what we are going to do is we will take a document, let's say D, and we will rank it according to our documents, other documents. Okay, with the relevancy. So document B can be most relevant to the document D, and document A can be second most relevant to the document D, and document C can be the third most relevant to the document D. Okay, so the data query is same, can be considered or should be, let's say, considered same as another document. Okay.
The query is a free text query. It means a query in which the terms of the query are typed freeform into the search interface without any connecting search operators.
Okay.
Step 1. Computing the term frequency, Tf. Frequency indicates the number of occurrences of a particular term T in document D, therefore.
Okay, so we will calculate the term frequency in each document. Okay, so you see, and TD is equal to number of times a term T occurs in document D. Okay, and okay, yes, this is the formula.
We can see that as a term appears more in the document, it becomes more important, which is logical. We can use a vector to represent the document in bag of words model, since the ordering of terms is not important. There is an entry for each unique term in the document with the value being its term frequency.
Okay.
Given below are the terms and their frequency on each of the document. N, T, D.
Okay, so in the first document, how many unique words we have? We have Ben studies about computers in computer lab. Each word appears one times. Okay, so the vectorial form of document 1 is, by the way, oh, they have okay, they did a normalization and removed the plurality from the word computer. So computer has frequency 2, Ben has 1, studies have 1, and lab has 1. They also removed the stop words. So what are the stop words here? In is a stop word. Okay. And about is also a stop word. Why these are stop words? Because these are generic words. Okay, they don't tell anything related to the document. Therefore, they are removed from the document. So they did normalization, they did pre-processing, and therefore the keyword in and about is removed. The computer keyword, computer word has become computer. So Ben has one frequency, studies have one frequency, one term frequency, computer has two, and lab has one. Okay, so this is the vectorial representation of document A, document 1. Okay, and so let's see the TF for document 2. In document 2, by the way, if you are applying some sort of rules, chain of rules, such as removing stop words or converting them to small case or making plural words to the non-plural, you have to apply same chain of rules to every document and your query as well. Okay, so whatever the rule applied is globally applied to every document and query. Okay, this is an important rule. Don't forget that. So the document 2 becomes Steve teaches Brown University. You see, they have converted every word to uppercase. Okay, instead of lowercase, they have converted them to uppercase. Either way is fine. You can either convert them to lowercase or uppercase. It's fine. It is up to your strategy. Therefore, both way should work. And these are the vector space representation, by the way, in bag of words model. When you are doing machine learning, you have to prepare vector representation of your whatever you are working on, your dataset features, because most of the algorithms work with vector representation of the data. So you see the term frequency is shown like this. However, the final representation has to include every word. Okay, so in your algorithm, if your algorithm supports empty vectors, you may provide the feature and its index, or you can give 0 to them. Okay.
Thus, the representation of documents as vectors in a common vector space is known as vector space model, and it's very fundamental to information retrieval.
Okay.
Since we are dealing with the term frequency which rely on the occurrence counts, thus, longer documents will be favored more. To avoid this, normalize the term.
Okay, so how do we normalize the term? Okay, we normalize the term by um, by dividing the term frequency to the total number of terms. Okay, shown as here. So the normalized term frequency becomes like this for band, studies, computer, and lab. Therefore, the total frequency, sum of frequencies are always equal to 1 in each document. You see, and the second document is like this, and the third document is like this. Okay. Okay, there are some Python code. You can write this in any programming language. Then the step 2 starts.
Step 2. Compute the inverse document frequency, IDF. It typically measures how important a term is. The main purpose of doing a search is to find out relevant documents matching the query. Since TF considers all terms equally important, thus, we can't only use term frequencies to calculate the weight of a term in the document. However, it is known that certain terms, such as is, of, and that, may appear a lot of times but have little importance. Thus we need to weigh down the frequent terms while scaling up the rare ones. Logarithms helps us to solve this problem. First of all, find the document frequency of a term T by counting the number of documents containing the term.
Okay.
Term frequency is the occurrence count of a term in one particular document only, while document frequency is the number of different documents the term appears in, so it depends on the whole corpus. Now let's look at the definition of inverse document frequency. The IDF of a term is the number of documents in the corpus divided by the document frequency of a term.
Okay, so the document frequency is the number of different documents that term appears. For example, we can explain it like this. The studies word appears only in one document. Computer appears in only one document. Lab appears in only one document. Steve appears on only one document. Let's see if there are any words that appears on multiple documents. This example is too simple actually. Yeah, every word appears only on one document. I would expect some multiple words appearing. Maybe we can find some sort of such example. Okay, let's continue with this example. However, let's say even if okay, so if this sentence were happen to be Ben studies about or this one, Steve teaches data science. Okay. Steve teaches data science at Brown University. If this sentence was Steve teaches data science at Brown University, the data word would have document frequency 2. Okay. And science still have 1. Okay, so you see, this would make the word data has document frequency as 2 because in the whole corpus it would have it would be appearing in two different documents. Okay.
It's expected that the more frequent term to be considered less important, but the factor, most probably integers, seems too harsh. Therefore, we take the logarithm with base 2 of the inverse document frequencies. So, the IDF of a term t becomes.
So the IDF becomes n over document frequency t within inside logarithma n was the number of documents containing term t. So for each term t in each document, we calculate a different, a unique Tf Idf value. Okay. So the IDF of computer is calculated as in logarithm total number of documents over number of documents with the term computer in it. So the computer init term number of documents is how many? It is 1. It appears in only one document, and this is the IDF. Total number of documents is 3. Therefore, there are 3 documents, and the log of 3 over 1 is 1.5849, and the turn frequency of computer is 1. Therefore, Tf Idf is this one. So you see almost all, actually all words in each document gets the same Tf Idf value. And then the Tf Idf scoring starts according to the query.
Step 3, Tf Idf Scoring. Now we have defined both TF and IDF, and now we can combine these to produce the ultimate score of a term T in document D. Therefore,
You see the Tf Idf score is calculated like this.
for each term in the query, multiply its normalized term frequency with its IDF on each document. In document 3 for the term data, the normalized term frequency is 0.167 and its IDF is 1.5849. Multiplying them together we get 0.2646. Given below is TF *IDF calculations for data and scientists in all the documents.
Okay, so the data word does not appear in document 1, therefore it gets 0. Does not appear in document 2, therefore it gets 0. And it gets this score in document 3. So, based on these similarity measures, by the way, after we have calculated Tf Idf scoring,
we will use any of the similarity measures, e.g., cosine similarity method, to find the similarity between the query and each document. For example, if we use cosine similarity method to find the similarity, then smallest the angle, the more is the similarity.
okay.
Using the formula given below we can find out the similarity between any two documents, let's say D1, D2.
Okay. So if you consider query as another document, it would be most related to document 3, then document 1 and document 2 will be same. Okay. The given sentences were too simple for this example. However, you should have already, you should understand the idea. Maybe I can find another example. So this is about ranking in machine learning. You rank different objects against each other. In text classification, you may use Tf Idf scoring for ranking. Okay, there is, yeah, this one is a better example. You see document 1 is machine learning teaches machine how to learn. Document 2, machine translation is my favorite subject. You see they have the same machine keyword. And the document 3, term frequency and inverse document frequency is important. So same again, we calculate the term frequency for each document. By the way, in this example they didn't do stopword is removable, so there is 2 is and other things. Next, we compute the normalized term frequency. Normalized term frequency is the term frequency of that document over the total number of words. Then we compute IDF. The IDF is computed for each term. By the way, the IDF is globally computed for each term. Okay, because what was the formula? The total number of documents and over the word having documents count. Okay, so the machine is calculated as 1.4y. The machine appears in 2 documents, therefore 2 over 3, 3 over 2 is 1.4, and others are like this. By the way, we also get the logarithm of that. Anyway, then we calculate Tf Idf for each word in each document like this, and then we can calculate Tf Idf score for any query we have. Okay, so the query is machine learning. You see the machine learning also gets computed Tf Idf based on the corpus itself. and you see we are using the IDF of these words in the corpus. So there is Tf Idf score like this. Then we can get the similarity for each document of machine learning. So the machine gets in document 1 0.4. Okay, and then we compute the query document similarity using cosine similarity. Okay, so they have used cosine similarity, and it is calculated like this. You see there is 0 in document 2 against query. Why there is 0? Because in document 2 learning keyword does not appear. Okay, so you can easily match them to values here. 0.4 multiplying with 0.7, and 0.7 is coming from the Tf Idf of machine in the query. So it is basically multiplication of Tf Idf scores and dividing them to other values according to cosine similarity. Then we get the similarity scores. So the query is has the most relation to the document 1, which is 0.94, and then 0.56, and then 0. So this is ranking of documents according to another document or a query. Okay, this is how it is done in information retrieval, in text processing. In other areas, it is same. Okay, whatever you use, you calculate some sort of distance or similarity, and based on that distance or similarity, you can rank anything, or you can order anything. Okay, this is about ranking in machine learning. Let's find if there is another useful article. Okay, information retrieval, we have already seen that. You see documents, indexer, index user query, top K retrieval, ranking model, learning model, training data, page results. In other areas, in machine translation for ranking set of hypothesis translation, in computation. Okay, let's see the other areas.
Learning to rank algorithms have been applied in areas other than information retrieval. In machine translation for ranking a set of hypothesized translations, 8 in computational biology for ranking candidate 3D structures in protein structure prediction problem, 8 in recommender systems for identifying a ranked list of related news articles to recommend to a user after he or she has read a current news article, 9 in software engineering, learning to rank methods have been used for fault localization, 10.
Okay, recommender systems are everywhere in nowadays. For example, Amazon recommends you products based on your history, search history, view history, purchase history. In Netflix, they recommends you movies based on your previous search history, view history, and other things. Probably they have tens of, maybe hundreds of parameters to recommend you the best results. They are not just that simple. They are combination of different factors. Okay, so feature vectors.
For the convenience of MLR algorithms, query document pairs are usually represented by numerical vectors, which are called feature vectors. Such an approach is sometimes called bag of features and is analogous to the bag of words model and vector space model used in information retrieval for representation of documents.
Okay, we usually convert them to feature vectors. It is analogous to bag of words and vector space model used in information retrieval.
Components of such vectors are called features, factors or ranking signals. They may be divided into three groups. Features from document retrieval are shown as examples.
You see how naming may differ. It may be called as features, factors, or ranking signals. They are all the same, however, different callings, different namings.
Query-independent or static features, those features which depend only on the document, but not on the query. For example, page rank or document's length. Such features can be pre-computed in offline mode during indexing. They may be used to compute documents' static quality score or static rank, which is often used to speed up search query evaluation. Query-dependent or dynamic features, those features which depend both on the contents of the document and the query, such as Tf Idf score or other non-machine learned ranking functions. Query-level features or query features, which depend only on the query. For example, the number of words in a query. Further information, query-level feature.
Okay, there are evaluation measures and such approaches, pointwise approach. Okay, let's see the approaches as well.
Pointwise approach. In this case, it is assumed that each query document pair in the training data has a numerical or ordinal score. Then the learning to rank problem can be approximated by a regression problem. Given a single query document pair, predict its score. A number of existing supervised machine learning algorithms can be readily used for this purpose. Ordinal regression and classification algorithms can also be used in pointwise approach when they are used to predict the score of a single query document pair, and it takes a small, finite number of values. Pairwise approach edit. In this case, the learning to rank problem is approximated by a classification problem, learning a binary classifier that can tell which document is better in a given pair of documents. The goal is to minimize the average number of inversions in ranking. Listwise approach edit. These algorithms try to directly optimize the value of one of the above evaluation measures, averaged over all queries in the training data. This is difficult because most evaluation measures are not continuous functions with respect to ranking models' parameters, and so continuous approximations or bounds on evaluation measures have to be used. A partial list of published learning to rank algorithms is shown below with years of first publication of each method.
Okay, you see they are starting from 1989, pointwise, listwise, pairwise, pointwise. You see they continue. There are so many different algorithms developed. Okay, practical usage by search engines. Let's read this as well.
Practical usage by search engines. Commercial web search engines began using machine-learned ranking systems since the 2000s decade. One of the first search engines to start using it was AltaVista. Later its technology was acquired by Overture, and then Yahoo, which launched a gradient boosting trained ranking function in April 2003. 33. Bing's search is said to be powered by RankNet algorithm. 34. Which was invented at Microsoft Research in 2005. In November 2009, a Russian search engine Yandex announced 35 that it had significantly increased its search quality due to deployment of a new proprietary MatrixNet algorithm, a variant of gradient boosting method which uses oblivious decision trees. 36. Recently they have also sponsored a machine-learned ranking competition, Internet Mathematics 2009. 37. Based on their own search engine's production data. Yahoo has announced a similar competition in 2010. 38. As of 2008, Google's Peter Norvig denied that their search engine exclusively relies on machine-learned ranking. 39. Quail's CEO, Tom Costello, suggests that they prefer hand-built models because they can outperform machine-learned models when measured against metrics like click-through rate or time on landing page, which is because machine-learned models learn what people say they like, not what people actually like. 40. In January 2017, the technology was included in the open-source search engine Apache Solr. 41, thus making machine-learned search rank widely accessible also for enterprise search. Vulnerabilities edit similar to recognition applications in computer vision. Recent neural network-based ranking algorithms are also found to be susceptible to covert adversarial attacks, both on the candidates and the queries. 42. With small perturbations imperceptible to human beings, ranking order could be arbitrarily altered. In addition, model-agnostic transferable adversarial examples are found to be possible, which enables black box adversarial attacks on deep ranking systems without requiring access to their underlying implementations. 42. 43. Conversely, the robustness of such ranking systems can be improved via adversarial defenses such as the Madry defense.
Okay, and ranking methods in machine learning. Okay, information retrieval, instance label, subset rank. Let's see if there is something important. Bipartite ranking. Okay, you see there are other ranking algorithms as well. This is a whole area of research, and you may even do a PhD on this area. Therefore, you just need to get basic idea at the moment, and when you encounter such problem, you may do more research. Okay. Yeah, this is explanation of lambda rank. Okay, these are whole articles that need a lot of time to understand. Okay. Okay, this is traditional ranking. We have already seen that. You see there are also academic articles. Okay. A machine learning approach to ranking RDF properties. Okay. Okay, all the idea is same in every case. You have to determine score, relevancy or distance between two documents, objects, whatever, and then based on that score, you rank them. You understand the idea. There is pairwise, listwise, pointwise. Take one candidate, compute score between candidate and query. Pointwise is the simplest and maybe the fastest one. Then there is pairwise. Take a pair of candidates, given a pair of candidates, decide which one will rank higher. However, in pairwise you have to do more computation. And there is listwise. Take the entire list, optimize its order. And you see there are the algorithms: soft rank, listnet, other rank, lambda rank. And in pairwise, rank take lambda rank. And anything that deals with regression problems, any algorithm. Okay, so let's, I think, read this article as well, because this one looks really good article. Yeah, I will read this article. Taking a pause. Okay. So the ABCs of learning to rank. Machine learning, natural language processing. Okay.
Learn how the machine learning method, learning to rank, helps you serve up results that are not only relevant but that are ranked by relevancy.
Okay. So let's see who is James Lee, the author. Looks like have some experience in machine learning. Okay.
Finding just the right thing when shopping can be exhausting. You can spend hours sifting through kind of related results only to give up in frustration. Maybe that's why 79% of people who don't like what they find will jump ship and search for another site. There has to be a better way to serve customers with better search. And there is. Learning to rank is a machine learning method that helps you serve up results that are not only relevant but are, wait for it, ranked by that relevancy. Search engines have been using learning to rank for almost 2 decades, so you may be wondering why you haven't heard more about it. Like earlier many machine learning processes, we needed more data, and we were using only a handful of features to rank on, including term frequency, inverse document frequency, and document length. So people tuned by hand, and iterated over and over. Now the data scientists are the exhausted ones instead of the shoppers. Exhaustion all around. Today, we have larger training sets and better machine learning capabilities. But there are still challenges, notably around defining features, converting search catalog data into effective training sets, obtaining relevance judgments, including both explicit judgments by humans and implicit judgments based on search logs, and deciding which objective function to optimize for specific applications. What is learning to rank? Learning to rank LTR is a class of algorithmic techniques that apply supervised machine learning to solve ranking problems in search relevancy. In other words, it's what orders query results. Done well, you have happy employees and customers. Done poorly, at best you have frustrations, and worse, they will never return. To perform learning to rank, you need access to training data, user behaviors, user profiles, and a powerful search engine such as SOLR.
So what may be SOLR? Open source enterprise search platform. Okay.
The training data for a learning to rank model consists of a list of results for a query and a relevance rating for each of those results with respect to the query. Data scientists create this training data by examining results and deciding to include or exclude each result from the data set. This vetted set of data becomes the gold standard that a model uses to make predictions. We call it the ground truth, and we measure our predictions against it.
Okay, you may heard gold standard or golden data when you are working with machine learning. It is the data usually manually evaluated and set by human evaluators, so it is being the gold standard. Okay.
Pointwise, pairwise, and listwise LTR approaches. The three major approaches to LTR are known as pointwise, pairwise, and listwise.
Okay, so the
Pointwise. Pointwise approaches look at a single document at a time using classification or regression to discover the best ranking for individual results. Classification means putting similar documents in the same class. Think of sorting fruit into piles by type. Strawberries, blackberries, and blueberries belong in the berry pile or class, while peaches, cherries, and plums belong in the stone fruit pile. Regression means giving similar documents a similar function value so that we can assign them similar preferences during the ranking procedure. During these processes, we give each document points for how well they fit. We add those up and sort the result list. Note here that each document score in the result list for the query is independent of any other document score, i.e., each document is considered a point for the ranking, independent of the other points. Pairwise. Pairwise approaches look at two documents together. They also use classification or regression to decide which of the pair ranks higher. We compare this higher-lower pair against the ground truth, the gold standard of hand-ranked data that we discussed earlier, and adjust the ranking if it doesn't match. The goal is to minimize the number of cases where the pair of results are in the wrong order relative to the ground truth, also called inversions. Listwise. Listwise approaches decide on the optimal ordering of an entire list of documents. Ground truth lists are identified, and the machine uses that data to rank its list. Listwise approaches use probability models to minimize the ordering error. They can get quite complex compared to the pointwise or pairwise approaches.
Okay, so you see algorithms, anything that deals with regression problems, algorithms rank net lambda rank, and algorithms soft rank list net other rank lambda rank for the listwise, pairwise, and pointwise. Okay, oh. Okay, let's continue.
Practical challenges in implementing learning to rank. You need to decide on the approach you want to take before you begin building your models. Given the same data, is it better to train a single model across the board or to train multiple models for different data sets? How do well-known learning to rank models perform for the task? You also need to decide on the features you want to represent and choose reliable relevance judgments before creating your training dataset. Choose the model to use and the objective to be optimized. In particular, the trained models should be able to generalize to previously unseen queries not in the training set and previously unseen documents to be ranked for queries seen in the training set. Additionally, increasing available training data improves model quality, but high-quality signals tend to be sparse, leading to a trade-off between the quantity and quality of training data. Understanding this trade-off is crucial to generating training datasets.
Okay, capture. Fusion AI captures and aggregates signals like queries, clicks, views, purchases, and other user behavior to create customized optimized experiences for each user. So you see their features are clicks, views, purchases, queries, and other user behavior. What may be that? Ratings, add to chart, queries, clicks, purchase history, past queries, language, loyalty program, direction of travel, previous location, current location, device, age, gender, job role, business unit, reviews, messages, ratings. So you see they have 3, 6, 9, 12, 15, 16, 20 features to process items and then rank them to show most relevant results to the user.
Microsoft develops learning to rank algorithms. The available options for learning to rank algorithms has expanded in the past few years, giving you more options to make those practical decisions about your learning to rank project. These are fairly technical descriptions, so please don't hesitate to reach out with questions. RankNet, LambdaRank, and LambdaMart are popular learning to rank algorithms developed by researchers at Microsoft Research. All make use of pairwise ranking. RankNet introduces the use of the gradient descent (GD) to learn the learning function, update the weights or model parameters for a LTR problem. Since the GD requires calculation of gradient, RankNet requires a model for which the output is a differentiable function, meaning that its derivative always exists at each point in its domain. They use neural networks, but it can be any other model with this property. RankNet is a pairwise approach and uses the GD to update the model parameters in order to minimize the cost. RankNet was presented with the cross-entropy cost function. This is like defining the force and the direction to apply when updating the positions of the two candidates, the one ranked higher up in the list while the other one down but with the same force. As an optimization final decision, they speed up the whole process using the mini-batch stochastic gradient descent, computing all the weight updates for a given query, before actually applying them. Lambda rank is based on the idea that we can use the same direction gradient estimated from the candidates pair, defined as lambda, for the swapping, but scaling it by the change of the final metric, such as NDCG, at each step, e.g., swapping the pair and immediately computing the NDCG delta. This is a very tractable approach since it supports any model with differentiable output with the ranking metric we want to optimize in our use case. LambdaMart is inspired by LambdaRank, but it is based on a family of models called MART, multiple additive regression trees. These models exploit the gradient-boosted trees, that is a cascade of trees, in which the gradients are computed after each new tree, to estimate the direction that minimizes the loss function, that will be scaled by the contribution of the next tree. In other words, each tree contributes to a gradient step in the direction that minimizes the loss function. The ensemble of these trees is the final model, i.e., gradient boosting trees. Lambda Mart uses this ensemble, but it replaces that gradient with the lambda gradient computed given the candidate pairs presented in lambda rank. This algorithm is often considered pairwise since the lambda considers pairs of candidates, but it actually has to know the entire ranked list, i.e., scaling the gradient by a factor of the NDCG metric that keeps into account the whole list, with a clear characteristic of a listwise approach. Learning to rank applications in industry. Wayfair. In a post in their tech blog, Wayfair talks about how they used learning to rank for the purpose of keyword searches. Wayfair is a public e-commerce company that sells home goods. Search is therefore crucial to the customer experience since Wayfair addresses this problem by using LTR coupled with machine learning and natural language processing (NLP) techniques to understand a customer's intent and deliver appropriate results. The diagram below shows Wayfair's search system. They extract text information from different datasets including user reviews, product catalog, and clickstream. Next, they use a variety of NLP techniques to extract entities, analyze sentiments, and transform data. Wayfair then feeds the results into its in-house query intent engine to identify customer intent on a large portion of incoming queries and to send many users directly to the right page with filtered results. When the intent engine can't make a direct match, they use the keyword search model. This is where LTR comes to the rescue.
Okay, so there is query intent engine, SECourses, entities query, classified ranking model, product aspect opinion sentiments. Okay. There is entity extraction, classified training, aspect opinion extraction, sentiment tagging, user reviews, product catalogs, and clickstream, natural language processing. All right.
In their keyword search approach, Wayfair issues the incoming search to produce results across its entire product catalog. Under the hood, they have trained a LTR model used by Solar to assign a relevance score to the individual products returned for the incoming query. Wayfair's then trains its LTR model on clickstream data and search logs to predict the score for each product. These scores ultimately will determine the position of a product in search results. The model improves itself over time as it receives feedback from the new data that is generated every day. The results show that this model has improved Wayfair's conversion rate of customer queries.
Conversion rate means that customers has purchased it or shown interest in the returned results.
Slack. The search, learning, and intelligence team at Slack also used LTR to improve the quality of Slack's search results. More specifically, they built a personalized relevance sort and a section search called Top Results, which presents both personalized and recent results in one view. Note here that search inside of Slack is very different from typical web search because each Slack user has access to a unique set of documents and what's relevant at the time frequently changes. Slack provides two strategies for searching, recent and relevant. Recent search finds the messages that match all terms and then presents them in reverse chronological order. Relevant search relaxes the age constraint and takes into account how well the document matches the query terms. Slack employees noticed that relevant search performed slightly worse than recent search according to the search quality metrics, such as the number of clicks per search and the click-through rate of the search results in the top several positions. Incorporating additional features would surely improve the ranking of results for relevant search. To accomplish this, the Slack team uses a two-stage approach, one, leveraging Solr's custom sorting functionality to retrieve a set of messages ranked by only the select few features that were easy for Solr to compute, and two, re-ranking those messages in the application layer according to the full set of features, weighted appropriately. In building a model to determine these weights, the first task was to build a labeled training set. The Slack team used the pairwise technique discussed earlier to judge the relative relevance of documents within a single search using clicks. This approach has been incorporated to Slack's top results module, which shows a significant increase in search sessions per user, an increase in clicks per search, and a reduction in searches per session. This indicates that Slack users are able to find what they are looking for faster.
Okay, you see they are continuously improving their algorithms and techniques based on the user behavior. Okay, this is important. They make changes according to that. New data.
Skyscanner. Skyscanner, a travel app where users search for flights and book an ideal trip, uses LTR for flight itinerary search. Search is complex and involves prices, available times, stopover flights, travel windows, and more. Skyscanner's goal is to help users find the best flights for their circumstances. The Skyscanner team translates the problem of ranking items into a binary regression 1. They label their data about items that users think of as relevant to their queries as positive examples and data about items that users think of as not relevant to their query as negative examples. Then, they use such data to train a machine learning model to predict the probability that a user will find a flight to be relevant to the search query. More specifically, the term relevance is defined to be the commitment click through to the airline and travel agent's website to purchase it, since this requires many action steps from the user.
Okay, so you see they are heavily utilizing the user behavior. You saw this, but you didn't buy it. You saw this, but you didn't buy it. You saw this and bought it. Therefore, this was relevant, and they analyze the shown results and make changes according to these results and improve their algorithm, their model. Therefore, next time they show the more relevant data to the user.
After applying LTR to the data, they do both offline and online experiments to test the model performance. In particular, they compare users who were given recommendations using machine learning, users who were given recommendations using a heuristic that took only price and duration into account, and users who were not given any recommendations at all. The results indicate that the LTR model with machine learning leads to better conversion rates. How often users would purchase a flight that was recommended by Skyscanner's model? These examples show how LTR approaches can improve search for users. All three LTR approaches compare and classify data to a golden truth set of data to determine how relevant search results are. As data sets continue to grow, so will the accuracy of LTR.
Okay. So this was a good article, and clustering and classification in e-commerce. Okay, so this was a topic of my PhD thesis. It is the clustering, especially, is extremely complex topic. Anyway, I will update our slides with the final and new slide. Okay. And Okay. There was another example. Okay, what was it? You see, it shows that my location, and based on that, Google displays me different results based on my logged account past behavior. This is sometimes good and sometimes not that good. For example, I am not able to find that article. I think this may be another one. Yeah, this one looks nice as well. Okay, I think this should be enough. Yeah, this one good. This one looks good as well. Okay, so let's make this bigger. All right, if you have any questions, please feel to ask me. And you should already decide what you are going to do in your final project and let me know whether it is good or not. In your project, you may get the raw dataset from internet, from dataset sources. However, you have to compose your feature set, your vector set, your feature set as vector yourself. Okay, so you will decide what will be the feature, what pre-processing or post-processing you will make. You will decide that. I don't want you to get something ready from the internet and do and show that as your project. Okay, I want you to understand how machine learning works. For you to understand it, you have to at least compose feature set yourself. You have to turn real life objects into the machine readable vectors yourself. Okay, this is what I want. You represent them in a correct way to obtain high accuracy or high relevancy based on your task. This is what I want. Okay, so let's upload our slide to the GitHub repository. Okay, hopefully see you next week.